In this video, I want to briefly review the rational root theorem. The rational root theorem is a tool for narrowing down the possible list of rational zeros of polynomial functions. Polynomial functions are functions that look like this in their most general form. A specific example might be f of x is 3x to the fifth minus 4x cubed, plus 2x plus 1. And so in this case, a5 would be 3, a naught would be 1, so on and so forth. So the rational root theorem applies to polynomials, and it's not just any polynomials. We do ask that every coefficient, all the AIs, are actually integers. So we don't want fractions or irrational numbers as our little coefficients there. And so what it says is, if you have a rational root, rational here meaning you can write it as a fraction of integers, we're assuming that your rational root is reduced, then the numerator p has to divide the constant coefficient, and the denominator q has to be a factor or a divisor of the leading coefficient. And just to be clear, you can get non-fraction answers. If x equals 3 was a root, you can view 3 as 3 over 1. So that's perfectly fine there. Last thing before we look at an example, I just want to make sure that we're clear here that when we say a root, we mean a zero of f of x. And so we could say that x naught is a root of f of x if and only if f of x naught is in fact 0. So rational root theorem lets you try and locate the rational roots of f. It may not have any, but it takes you from infinite possibilities down to a much smaller list, which you can then check one by one. So let's do an example here. In example 8, we're going to list the potential rational roots of this function. And so I know that my rational roots are going to be factors of 4 divided by factors of 1. And where you put the plus or minus is up to you. For the first part, I'm just going to put it in front of the list of factors. You don't have to do this next step if you don't want to, but it might be helpful. I'm going to list out all the factors, the divisors of 4. They are 1, 2, and 4. And 3 is prime, so divisors of 3 are 1 and 3. And so my list of possible rational roots is going to be anything in the numerator over anything in the denominator, all possible combinations there. And so let's make the list here. We would get plus or minus 1 over 1 is 1, right? Anything over 1 is 1. So I'm going to get a 2 over 1 and a 4 over 1. That's just going to give me plus or minus 2, plus or minus 4. Then I'm going to get 1 over 3, so plus or minus 1/3, plus or minus 2/3, and then plus or minus 4/3. That's the list of possible rational zeros for this polynomial function. Now, it's quite a list, so if you actually want to find them, you're going to have to go through and check. There's really no need to check these guys first. You always want to check the easier zeros first, and then hopefully as you find one or two, you can then factor at some point and not have to keep looking. So let's use synthetic division to actually break f apart into its factored form. So what I would do is I'm going to start with the most obvious and easy root to try, which is plus or minus 1. I'll do actually x equals 1. And I'm going to write down 1, and I put a little sideways bracket around it. This is for synthetic. I'm going to write down the coefficients of my polynomial. So I'll write down a 3, a -2, a -5, and a 4. I like to leave a little space and draw a line. And if by some chance there was no 5x term here, if it just went minus 2x squared and 4, I would actually write a 0 there. So you do need to keep placeholders for all of those spots. If you're missing a term, just put a 0 there. So the way synthetic works is you drop the first coefficient. The 3 just comes down. Then you multiply 1 times 3, and that answer goes here. I get 3. And then I'm going to add those two, and the answer goes right there. So I'm going to get out a 1. 1 times 1, that's going to go here when I multiply. 1 times 1 is 1. I add, I get -4. 1 times -4 is -4. That goes there, and I get a 0. And when you get a 0 as your last term, that's success. That means that x equals 1 is a 0. It is a factor. So we did that. And actually the synthetic division is even better. It actually tells you how to split it. So you can write down f of x is x minus your 0, so x minus 1. You're going to drop degree by 1. This is a factor of degree 1, so your original degree, which was a cubic, is going to become a quadratic. And the coefficients of your quadratic are sitting right there. So you're going to have 3x squared plus x minus 4. And at this point, you could keep doing synthetic division to hunt for the other roots, or you could just factor. I'm going to quickly factor this thing. I'll do the AC method. AC is what, negative 12. And so I want factors of negative 12 whose sum is 1. So how about 4 and minus 3? So when we split this thing, we know it's going to be a 3x and an x. I'll do a minus 1 and a 4, and that does it. I factored it. You can check that. So f of x is x minus 1 squared times 3x plus 4. If you wanted to look via synthetic division, you could actually try 1 again. We can see 1 is a repeated root, so I can try 1 again on this quadratic. Is 1 a 0 of this quadratic? So I would write down 3, 1, and minus 4. Leave a space, drop a line. The 3 comes down, I multiply, and I get 3. Add, I get 4. Multiply, 4, 0. And you can see that I'm left with x minus 1 times 3x plus 4, which is exactly the factors that we got. This part is unnecessary. It's much better just to factor the quadratic directly, but it does work.